Hello, let's continue making a 3D graphics engine. Now there's a lot to get through in this video, so I'm going to be picking up the pace quite a bit. And here's a quick preview of what we're going to be aiming for today. We're basically going to be looking at camera control and clipping of triangles, so we can render triangles that go behind the camera and off the screen. And you can see I've got a fun little demo where we're navigating a terrain. And as usual, we're going to be starting off with exactly the code we finished part 2 of the series with, where we looked at normals, culling, lighting and object files. If you've not seen parts 1 and 2, then I suggest that you watch those before watching this video. There's a lot of background information that's required in order to understand how this code works. But before we get started, I wanted to address an ongoing design philosophy, which I think is starting to slow down our productivity. And that is, we're having to do everything for X, Y and Z components separately. We're doing all of the maths line by line. And this is starting to make the code a little unwieldy, so I thought I'd wrap it up in a vector class of its own and have a matrix class. And so started a little adventure in indecisiveness. Here you can see I've actually created a vector class where it's got methods for the common routines, and I'm using operator overloading so we can simply add vectors together and scale them in a nice and simple way. I even created interactions for vectors to work with matrices. And this worked very well until I realised, well hang on, I'm going to have to explain all of these concepts, operator overloading and things like this. And I will do, but not in this video, it's not really part of this series. So then I implemented a second approach. This time I implemented the graphics engine using GLM, which is a mature and stable vector and matrix library created by the people that make OpenGL. And this worked very well too, but I kind of feel that it goes against the code it yourself philosophy. There's nothing wrong with using third-party libraries for stuff like this. Indeed, I use this library for my professional applications. And I was discussing my dilemma on the Discord server with my friend Jack. I couldn't decide, should I create my own matrix vector library, which is a little bit reinventing the wheel, or should I use a third-party library instead? And he very insightfully said, well, if your goal is to learn about wheels, then there's nothing wrong with reinventing the wheel. And I agreed, but I didn't want to go as far as doing operator overloading and things like that. And the reason being is I know quite a few of you have taken this code and implemented it for other platforms, so luxuries like operator overloading might not be available to you. So I've come to what I believe is a happy medium. Rather than making specific modifications to the vector and matrix classes, I've decided to create a bunch of utility functions to add to the main class. We did actually do this already with the existing code, but I thought I'd try and make them a little bit more consistent. So for example, to add two vectors, I created the vector add function that takes the two vectors as inputs and creates a new vector as the output. And I will fully hold my hands up and say that I've made no attempt to optimize this code at all. I want it to be educational and informative, not obscured due to optimization. And so if you have a vector add function, you also need a vector subtract function. And how about scaling functions where we can multiply and divide? We know the dot product is important, so we'll have one of those too. And since we've got the dot product, we may always have normalizing and getting the length of a vector. And we know from the previous video when we've been creating normals, the cross product is quite useful to have too. We already have this multiply matrix vector function, but it does some weirdness in here to normalize the final result. I want my new library to be quite consistent, so I'm going to replace multiply matrix vector with matrix multiply vector. But you'll notice that this has introduced a fourth term requirement into the vector class. So we'll need to add that too. As with the vector utility functions, there's quite a few matrix utility functions we might need. We can create an identity matrix. And how about the three rotation matrices we've already looked at in the previous video? Translation matrices are also useful. And in the very first video we looked at constructing projection matrices, so I'll capture that as well. One important function when you're having a matrix library, which we've not done yet, is matrix-matrix multiplications. So I'll include that. And there's one more which we'll develop during this video. So now that we've got this library of functions, it's time to convert the existing code over to this new way of doing things. So in onUserCreate, we no longer need to manually create the projection matrix, we can just call the function to do it for us. I'm also going to remove the spinning cube code now. I think we can do things a little bit more sophisticated than cubes. Now we can load object files. Naturally, we don't need to create these rotation matrices anymore. We can call our function to do it for us. The new utility functions also allow us to do things in a slightly more optimal way when we're drawing the triangles. So instead of doing the individual matrix vector multiplications, we can create a single matrix called our world matrix that contains all of the transformation information required before we draw our object. And so once we've got our two rotation matrices, we can create a translation matrix and we can create what is called the world matrix. It's important that we get the order of multiplications correct, so firstly I'm rotating around the origin and then I'm translating the object to a different location. So instead of requiring these intermediate states, I'm just going to have a transformed state. And I can replace all of this code with simply 3 lines to multiply each point of the triangle by the world matrix. The next section of code was used to calculate the normal to the triangle, so we could work out various properties of the triangle. Can we see it, and what colour is it? Well, we can replace all of that code now with a simplified form using the utility functions. I told you this video was going to go quickly. We have a lot to get through. To see if the triangle was visible, we cast a ray from the triangle to the camera and did a dot product between that ray and the normal. We can do this now in a simple couple of lines. And it's a similar story when we were trying to calculate the illumination. The original tri-translated triangle has now simply become tri-transformed. The next stage was to project the transformed triangle to a projected triangle in 2D space on the screen. That's pretty similar to what we're doing here, except the arrangement is a bit different. Now, if you remember, the revised matrix multiply vector function no longer normalizes the coordinates, so we have to do this manually. But fortunately, we have a vector divide function to help us do that. And we can do a similar trick to do the offset of the screen space to the center of the screen. We added an additional component, and more often than not, we're going to want this additional component to be equal to 1. So I'm going to set up the default constructor of the struct to initialize these values appropriately. And so let's take a look and run this, and we can see it behaves exactly the same way as before. I appreciate that was quite a fast run through of the code, but functionally nothing has changed. All we've done is refactor it a little bit to make it a little more user-friendly. I recently reached out to my followers on Twitter and said what object would they like to see in the next video. And Teapot won, and there's a reason somebody chose Teapot. It's a very nice teapot. In fact, this is called the Utah Teapot, and it's one of those hello world moments of 3D graphics. If you can display a teapot, specifically the Utah Teapot, you know that you're kind of doing things right. And I recommend that you look up on the history of the Utah Teapot if you want to know a little bit about how graphics rendering worked way back when and how much it's evolved since. But in a nutshell, the Utah Teapot can be described with just a simple set of geometric primitives. Curves, splines even, and we know we like splines on this channel. So that's just a little friendly shout out to my supporters on Twitter before we move on to something a little bit different. The dot product, again. In the previous video we considered the dot product to be a measure of similarity between two vectors. And whilst this was sufficient for explaining the phenomena we were interested in at the time, I now think it's time to explain what the dot product really means, and it is to do with how one vector projects onto the other. So let's take two vectors and let's look at how v1 projects onto v2. And the simplest way to look at this is to draw a normal to v2, which is of course at 90 degrees. And this distance here is how much v1 has projected onto v2. And we can assess the relationship with similarity in the first video by considering the angles that are taking place here. If we assume that v2 is actually a unit vector, i.e. its length is 1, and we take the angle between the two vectors, and using the fact that it's a right-angled triangle and we know the length of one of the sides and the angle, the relationship becomes quite clear. we know that cos of theta equals the adjacent side, the d that we're looking for, over the hypotenuse. But in this case, the hypotenuse is the length of v1, the magnitude of v1. And with a simple bit of rearranging, we can see that the magnitude of v1 multiplied by cos theta equals d. And this is how we could see if two vectors were similar or not. Because if we've got one vector pointing that way and one vector pointing that way, the theta is very small. But if we've got one vector pointing that way and one pointing this way, the theta becomes very large. Fortunately, because vectors are awesome, we don't need to worry about theta. And so we can define the dot product as simply being v1 dot v2 over the magnitude of v2. Because don't forget, v2 needs to be a unit vector. And more often than not, whenever we're calculating the dot product between two vectors, we're using unit vectors anyway, so we often don't need to do this part. I feel it's important to understand that dot products actually represent projection, because we're going to be using them a lot to talk about the next segment, which is camera control. Fundamentally, there are two ways to think about camera control. Firstly, we can move the camera around the world, represented by the man moving around this forest, and that intuitively makes sense. An alternative way is we can move the whole world around the man. And both are completely valid approaches. Essentially, our camera is always at 0, 0, 0, the origin of the world. And so we could go through every object in the game and translate them to a different location to give the illusion that we're walking through that world. However, this can get a little bit tricky when it comes to rotation, because the centre of rotation for all of these objects changes. And so I think it's a better approach to represent the camera as an object in the world and create some sort of transform which we can apply as part of our model and projection transformations, which represents how the camera interacts with the world. Now, before we delve too deeply into cameras, I want us to think about a different way of representing rotation. We saw in the previous videos we used a simple rotation matrix which used a theta value and sine and cos in the appropriate places to give us a transformation, so we could transform a point from one location to the other, rotating it around the origin. And sometimes when working with angles, things can get a bit tricky. So the system I'm about to derive I'm going to call a point-at system, and this is the effect that we're looking for. Let's assume I've got an object in 2D space. My object will have an origin point and a vector that represents the forward axis of the object. Let's say I wanted this arrow to point at something in the scene. One option is, of course, I can specify the angle theta between the forward direction and the direction where the point is. But I want to avoid using theta. Instead, what I'd rather say is, well, hang on, please just look towards or point at that location. I.e., I want to come up with a transformation which converts this forward direction to this forward direction. So I can just express the look at direction as a vector. And we can extend this idea even further. Instead of assuming that we're doing everything around the origin, if I assume this is our eye point, I can place the object anywhere in the 2D plane and tell it to look at another location. And conceptually, I feel this is much simpler to think about than working out the angles and the trigonometry. So here I've got an axis in 2D, and I'm going to make the assumption that everything we can do in 2 dimensions, we can do in 3 dimensions by simply adding an additional term. On here, I've got y and x. And I'm going to place a point P at location 1, 1. With a rotation matrix, I would create a mapping between the space outlined in black and the space outlined in red, and this would be by angle theta. This means my point P would also rotate to a new point, which I'm going to call Q. And what I want to work out is, where does Q exist in the original space outlined in black? But instead of specifying theta, I'm going to designate one of my axes to be the forward direction. In this case, it's going to be x. And I'm going to represent that direction as a unit vector. Once we have the forward vector, we know that anything that is perpendicular to that forward vector must also represent then the equivalent y-axis. So we can generate the unit vector to represent the other dimension. And so in this rotated space, our point Q still exists at 1, 1. But clearly in the original space, the location of Q has changed. Once we have the unit vectors for our new space, we can break them into their individual components. So along the bottom here, this distance I'm going to call AX, and this distance AY. And we can do the same for the other axis. I'm going to call this one BX, and this one BY. If we look at where Q exists in the new space, and where P exists in the new space, I'm going to carry these on beyond the axis. We can see that this distance here is in fact P's x coordinate times AX. Now P we've left at 1, 1, so it's just simply AX. And this distance here is P multiplied by BX. So what we're effectively saying is QX equals AX plus BX when P is at location 1, 1. And it follows then that QY equals AY plus BY. Again, when P is 1, 1. We can extrapolate that if P was at 2, 1, we'd need 2 lots of AX. If P isn't 1, 1, we can scale these values accordingly. So we end up with QX equals PX AX plus PY BX. And QY becomes PX AY plus PY BY. And so, by declaring a vector as being the forward direction, calculating a vector which is normal to that in the same plane to give us an opposing axis, decomposing those vectors into components in the space of the original axis, and scaling those components accordingly, we can come up with a mapping that is effectively a rotation, and all we've needed to supply is the direction that we're declaring as forward. When we have a set of equations like this, we probably want to try and represent it as a matrix. So we can think about it like this: Px, Py multiplied by Ax, Ay, Bx, By. And if you remember from previous videos, when we're multiplying out this matrix, it's Px times Ax plus Py times Bx becomes Qx, and likewise for Qy. So in 2D space, we've come up with a simple way of rotating the space based on a direction vector. But this has so far assumed that we're doing things rotating around the origin. What if we want to rotate around a point in space? Well, as with 3D, if we want to do translation, we need to add another component to our vector and our matrix. So let's assume the point we wish to transform is now Px, Py, and 1. We're going to need a 3x3 matrix now to do the transformation. Well, we know already that the top of our matrix is what we've already got: Ax, Ay, Bx, By. And because we want to do a translation, all we want to do is offset the coordinates. So this will be values multiplied by the 1. So we'll say Tx and Ty, our location in 2D space. Our third column will fill in as 0, 0, 1. And so now all we need to do is specify a forward vector, derive an orthogonal vector, and provide a translation offset. And we've derived in 2D a matrix which will transform any set of points according to these criteria. And it goes without saying that for 3D it's a very similar format, except we've now added a z component to the point. But we also need an additional vector in our 3D space. And so here we can start to see a mapping. Let's assume we've got our A vector, which is our forward vector. We've got a B vector, which is orthogonal to our A vector. And we've got a C vector, which is orthogonal to both. And finally, we can offset our origin point by point T. And I'm going to call this the point at matrix. And it's common to name these somewhere along the lines of forward, right, and up, although the ordering of these may change on your application. We can use our point at matrix to position and rotate an object in our world space, like any of the other matrix transforms that we've been doing. And this in itself is very useful. It can make the scene look lively and interactive. We can have objects that follow and look at other objects in the game. And so far in the videos, we've always assumed that the player or the camera is at location 0, 0, and it's looking down one of the axes. In 3D it would be Z, but in this 2D example, it's looking along the X-axis. But since we now have a transformation where we can use the direction and a point, it would be ideal to use this as a camera. The point at transformation has worked out how to transform from the origin point to this location. But a camera needs to do the exact opposite. It needs to take all points anywhere in space and transform them back to our original 0, 0 looking along a single axis. We want, effectively, the inverse of whatever this transformation was. And before I go any further, I am not going to talk about how to invert a matrix. It is well beyond the scope of these videos. Fortunately for us, and this only applies to matrices that can rotate and translate, if you're scaling this won't work, there is an established routine for inverting this matrix. And I've drawn it out here, and I'm just going to treat it completely as a mystery black box. So please note, this isn't the correct procedure for all 4x4 matrices, this only works in this instance. And visually it's quite nice, because we can see that our A, B, C and T vectors still exist in the inverted form, they've just been transposed. But our translation vectors, they now become the dot product between our translation point and one of our axis vectors, subtracted from 0. And so whereas before this was our point at matrix, I'm going to call this one our look at matrix. And so once we have transformed any object's coordinates into world space, we can multiply it by this matrix to translate it into view space, i.e. looking through the lens of a camera. And we can position that camera anywhere in world space, and we can make it look at almost anything in world space. And so now I think it's time we add a simple first-person shooter-like camera to our engine, so we'll be able to walk forwards and backwards and rotate on the spot. We'll also add in up and down so we can get some elevation in our scenes to inspect them from different perspectives. I always find it useful when working with cameras to have a 3D object that represents the axis and the directions of those axes in space. Because when you start playing with cameras, things get weird quite quickly and can often become inverted. I'm also going to confuse myself by allowing the world to spin round relentlessly, so I'm going to remove the theta update. I'll still apply the rotations, there'll just be no rotation occurring. So let's take a look. And, well, we can see something perhaps that resembles an axis. Certainly, it looks like the graphs that I draw in OneNote. I'm going to add now an additional function to our matrix utility function set called matrix point at, which as we've just seen requires a position vector where the object should be, the target vector, this is kind of the forward vector for that object, and an up vector. Creating the forward vector is easy. I simply subtract the position vector from the target vector and normalize it. Even though we've provided an up vector as part of the input to this function, the actual up vector might change because our new forward vector may have a y component that gives it some elevation. Effectively, this is the equivalent of pitching, i.e. the scene rotates along the x-axis. We can create a new up vector by looking at how much of our described up vector projects onto the new forward vector, and we can adjust the described up vector accordingly. Creating the new right direction is quite easy. As it says here, it's just the cross product of those two new vectors we've just created. I'm then going to manually construct the point at matrix we've just seen in the slides. If we invert the point at matrix, we can create the look at matrix. And this inversion only works for this specific type of matrix, but I've created a function here called quick inverse, which simply does that inverting for us. This means we can now add a camera matrix into our transformation chain. We'll have an up vector which we can define as 0, 1, 0, so that's pointing up the y-axis. We already have a camera vector, but I'm going to add an additional vector called look direction. And ideally this will be a unit vector that travels along the direction we want the camera to point. So along with our up vector, I'm also going to create a target vector, but I'm going to set the target location to be the current camera location plus the look direction. And we'll just hard code the look direction to be 0, 0, 1 along the z-axis. I now have sufficient information to define a camera matrix, where I'm going to call my matrix pointAt function and provide the current camera location, the current target point the camera should look at, and our up direction. But to make it behave like a camera, what we want is actually the inverse. So I'm going to call our matrix quick inverse function and pass it the camera matrix. And the result of this function I'm going to store in my view matrix. We now have an additional stage in our transformation pipeline. So I'm going to add a triangle viewed to this. And so before we project the triangle, we no longer want to go directly from world space straight to projection space. We want to go through our view matrix. So we'll multiply our transformed triangles by our view matrix into our new viewed triangle. And of course this means we want to project our viewed triangles instead of the transformed triangles. So we'll just have a quick test to see if that works, and it looks exactly the same. The only way we can test our camera is to add some user input that will allow the player to move the camera around the scene. So here I've added up and down keys, which will increase or decrease the camera's Y position. I press up and I press down. We can see the object is moving. In fact, we can even see underneath the object, and we can see it is actually an axis, so that's pointing along the Z axis. At the top here, we've got the letter Y. I'll also add in left and right, so we can see what happens along the X axis. So I can move up, and I can move from side to side. And very nicely, we can start to see the axis pointing which direction is which. And this is quite nice because all we're doing is moving the camera around the scene. We can intuitively think about where to place the camera and how to move it around. If we want to create a first-person shooter style camera, a very simple one that is, we need to think about what direction is the player facing. And this is effectively a rotation in the y-axis, or yaw. It's traditional to use the W, A, S and D keys in a first-person shooter. And so if the user presses the A key, I want them to turn left, which means decreasing the yaw value. Conversely, if they press the D key, I want them to turn right, by increasing the yaw value. Moving the camera forward and backwards is a little bit more involved, because I want the camera to travel along the look_dir vector that we created before. So I'm going to create a temporary vector called v_forward, which is a scaled version of the look direction, and it's scaled by the speed we want to move at, because we can assume that look direction in this case will be normalized. And because we've integrated time into this, we've effectively created a forward velocity vector. So in order to move our character when the W key is pressed, we want to add to our camera's location this velocity vector. And likewise, we want to do the exact opposite for when we're moving backwards. We subtract the velocity vector from the current camera location. So what do we do with this yaw value? Well, our pointAt matrix requires a forward vector, which we've currently set as target. However, our forward vector is actually going to be rotated by the yaw value. So if I specify this to be a fixed vector, just heading along the z-axis, and I create a rotation matrix to rotate around the y-axis yaw radians, I can rotate my target vector by the rotation matrix to produce a new look direction vector. So I can remove this line. And so this vector is some unit vector rotated around the origin, but now I need to offset that to the current camera's location. So in brief, we take a target vector fixed along the z-axis, we rotate it by yaw radians, which simulates turning the player from left to right. From this, we get a new forward-facing vector, which we add to our camera location to give us a target for the camera to look at. So let's take a look. Well, we've got the scene, and I'm going to move the camera up a little bit first, and now I'm going to walk backwards to zoom out a bit. And we can see the axis is very clear. If I move to the left and right, I can steer, I can move the camera backwards, forwards. I'll just move it down a little bit. There we go. So that's, oh dear, dearie, dearie me. Oh no, what's gone horribly, horribly wrong? Well, we've been struck with the same problem we saw in video 1 when the objects got too close to the camera. When we're projecting the triangles, they have a Z component which we divide by, and as that Z component gets smaller and smaller and smaller, of course, whatever we're using it to divide by gets larger and larger and larger. Our triangles get huge because Z approaches 0. And this causes a problem for us, because our triangles are so big, when we're trying to draw them, we're getting all sorts of memory corruption errors, we're getting performance problems because there are literally billions, if not trillions, of pixels to try and draw. The second problem is that sometimes the triangles will now exist behind the camera, and I just can't comprehend what that means. This means we need to get in control of our triangles again. We're going to need to clip them, the process of chopping a triangle up into smaller shapes. Before we start talking about clipping, I think it's worth thinking about the differences between programmers and mathematicians. Consider in 2D space we have a line. Now as young people, one of the things that we're taught to represent lines is y equals mx plus c. And this is nice for programmers because we can sequentially go through x, create y values and plot a line. Mathematicians don't think like this. Instead, what they see is a concept where there is a state where all of this is true. And so in the infinite soup of x and y coordinates, there exists only one set of solutions that can satisfy the truth of this equation. And it just so happens that all of those solutions lie along the line. If we consider that m is really dy by dx, which is effectively a vector following the gradient of the line, we can rewrite this equation as being y equals dy by dx x plus c. And therefore it follows that y dx equals dy x plus c, and finally minus dy x plus y dx equals c. Let's suppose for a moment that instead of having a gradient, what we actually have is a normal to the line. Well, inverting a gradient to a normal is fairly well established. Dy by dx, if we wanted to invert that, becomes minus dx over dy, which we can say is the same as nx ny. And this is quite useful, because here we've got a dy, and we're saying that's the same as minus our normal x value. So let's replace that in our formula. And whilst we're at it, we'll take our dx value, which is the same as our normal y value, and replace that in our formula too. So this means we can represent our line as x normal x plus y normal y equals c. Now c is traditionally the point of y-intercept. But remember, this equation actually represents the set of all solutions that lie along this line. So we can pick any x and y value which we know lies along this line, and therefore it must be true. So let's pick a point that lies somewhere on our line, point P. So we know the location of one valid solution exists somewhere along the line defined by xnx plus yny equals pxnx plus pyny. And this is quite a nice form to have it in, because it simply becomes xnx plus yny minus p dot product n equals 0. And so wherever this condition is true, in 2D space, our line will go through. And this means just by knowing a single point on our line and the normal to our line, we can represent a line. And intuitively this makes sense. So let's say I've got a normal that's slightly different, goes up here, then my line goes like this. Let's say I've got a point up here somewhere, point P, and my normal is pointing in this direction. Then my line is doing something like that. And as we saw before with the matrices, extending to 3 dimensions is quite simple. We just add in the z term. But it's not a line anymore, it's a plane. An infinitely large sheet or surface where all of the solutions that satisfy this equation lie. And here we can see that this is in fact the standard plane equation. Ax plus by plus cz take d equals 0. And it's nice to work in this format, I think. Firstly, because it's quite intuitive to visualize the plane or the line in the appropriate spaces. But also, it works with things that we're already familiar with. We've got normals and we've got points. And that's all we need to represent quite a sophisticated geometric primitive. So let's get back to graphics and start thinking about clipping. And I'm going to show this in 2D because it's easier for me to draw. But firstly, let's assume we've got a line. And I've got a situation where I want to draw a triangle. And everything on this side of the line I want to keep, but everything on the other side of the line I want to get rid of. Given the original points of my triangle, and now the intersection points between the edges of the triangle and the line I'm using to clip against, you can see I've formed a quadrangle, a 4-sided shape, and they're no good to us in this engine. So in this configuration, I need to split that into 2 triangles. There is, perhaps unsurprisingly, a second configuration. I've got my 3 points and my 3 triangle edges. This time I don't want any of this, but I only form 1 additional triangle once I've clipped it. So this implies there's a bit of an algorithm that we need to do. I'm going to need to count how many points lie on the inside of the line I want to clip against and how many points lie on the outside. So in this first example, we can see we've got 2 points of the triangle that live on the inside. So I want to count inside points. As a byproduct of this, we're also going to be able to get the outside points. There are 2 additional scenarios. If I have a triangle whose all 3 points lie on the outside, then I want to clip the whole triangle. I don't want to do anything. And conversely, if I have a triangle whose has all 3 points on the inside, I don't want to do anything either. I just want the triangle to go through untouched. So we need to classify how we're going to break up the triangle. If inside is equal to 3, then do nothing. And therefore, if inside is equal to 0, well, we still don't need to do anything, we just need to reject the whole triangle. If inside equals 2, then I need to form a quad. So that's 2 additional triangles. And finally, if inside equals 1, then I'm just going to form a new triangle. So I think we're going to need a clipping function which is capable of returning 0, 1 or 2 triangles, depending on the scenario. If I'm returning a single triangle, I can form that triangle out of the original inside point, and the 2 points where the original edges of the triangle intersect with the line that we're clipping against. And it's important to remember to maintain a clockwise order, because as we've seen in the previous videos, we use the winding order of the triangle to determine which direction its surface normal faces. In a similar way, if I'm producing 2 additional triangles, I can take the 2 original inside points and create the first triangle using the intersect point between one edge and the line we're clipping against. The second triangle needs to be thought about to ensure its winding order is correct. We can take the original point and then the 2 new points. That ensures we've got a clockwise winding order. However, this isn't quite the end of the story. We want to clip triangles against the edges of the screen, which we can easily define using normals and points. But let's assume I have a situation like this, where I have one big original triangle that needs clipping against multiple edges. This is quite a common scenario, and we need to think of an algorithm for handling clipping against multiple edges, but we must remember that each time we clip, we're forming either 0, 1 or 2 additional triangles. So let's start with this edge. Don't forget that our clipping planes are essentially infinitely long, and we're only clipping against this one plane. So ignore the others for now. Those points are still valid. They're on the inside of this clipping plane. which means once this triangle is clipped, the solution is actually forming a quad, and as shown, means forming two additional triangles. Therefore, we remove the bit on the other side of the clipping plane. Now let's take our second edge, the one at the top. Well, one of the triangles, we can see entirely that its 3 points lie on the positive side of the clipping plane, so we don't need to do anything with that. But we don't want to ignore it, so that needs to go past through our clipping algorithm function. However, yet again, we're going to form a quad with the other triangle, and we can get rid of the stuff on the negative side of our clipping plane. Now our third edge is starting to look a little bit more complicated. We've now got 3 triangles in existence. This triangle, all of its vertices lie on the positive side, so that one can pass through. However, as before, we're going to have to break up this larger triangle into a quad. And we also have an additional triangle. It's only a little bit down here, but still, that also needs to be split into a quad. Our final surface we must use to check, but we can see now all of the triangles that remain lie on the positive side, so there's no clipping needs to occur here. And our original triangle has now been split into 1, 2, 3, 4, 5 additional triangles. All of these triangles share the same properties as the original triangle, so the colour information doesn't change. The complexity of this part of the algorithm is not necessarily in the clipping. It's in the fact that the byproducts of clipping can result in a multiple number of new triangles. And so we'll create a clipping function that returns the requisite number of triangles in order to satisfy the clip, and we'll add those triangles into a queue to be processed further. Fortunately, we know that once we've clipped against one edge, there will be no further triangles created that need testing against that edge. So all remaining triangles, as a consequence of the clip, need to be tested against the remaining edges that we're testing. It's getting a bit complicated, this. And so I'm going to show in pseudocode how I implement this algorithm. I'm going to create a queue, and to that queue I'm going to add the triangle that needs clipping. And then for each plane in the set of planes I wish to clip against, I'm going to test the triangles in the queue. I'll then remove from the queue the triangle at the front. I'll then test this triangle using the clipping function against the plane, and this will yield 0, 1 or 2 additional triangles. Once I've gone through all of the triangles in the queue, I'll have a list of new triangles. So I want to now replace my queue with this list of new triangles. And I know that none of these new triangles need to be tested against that plane again. And I quite like this approach, because once it's finished running, queue will only contain valid triangles that should be rendered to the screen. They'll have been clipped against whatever planes we need them to be. But it also guarantees sort of the minimum number of checks required for a triangle to be clipped against the planes. So let's go and implement this in code. But note, I'm going to do everything with planes, so even the screen edges, even though they're technically 2D, since I've done the algorithm for a plane, I might as well just use it. I'll add 2 new entries to our utility functions. The first is a function to test and return the point where a line intersects with a plane. And as you can see, we're providing the point on the plane and the normal to the plane to define the plane equation. And we're providing the starting point and ending point of a line. The function will return a vector if the line crosses the plane. And rather than derive all of this, because I'm aware the video is getting horribly long, this is absolutely nothing clever. It is a very standard and easy to find algorithm online. How do lines intersect with planes? All I've done is implement it using our utility functions. The second function I'm going to add is our clipping function, and this has quite a complicated definition. Firstly, it returns an integer. That's how many triangles are going to be returned by this function. We provide the plane equation parameters, the position and the normal, and we provide a reference to the triangle we're trying to clip. Now we know we can get either 0, 1 or 2 triangles out, so I'm providing those via references as inputs to the function. We'll either return nothing here, or the first triangle will be useful, or both triangles will be useful. A little bit of housekeeping just in case. The first thing we're going to do is make sure that the plane normal is indeed normal, because that's fundamental for any of these equations working. Now, to classify whether a point is on the inside or the outside of the triangle, the easiest way to calculate this is to calculate the distance between the point and the nearest point on the surface of the plane. We can look at the sign of this distance to indicate whether we're on the inside or outside of the plane. So I'm going to create a little auto function to do this for me, and you'll start to see some very familiar looking maths. To classify whether the triangle is inside or outside, I'm going to need to store some information about the points. So I'm going to create two, in this case, fixed arrays to store pointers to the points that lie on the inside or the outside. I'm also going to keep a reference of how many points I've counted so far, because next I'm going to take each point of my triangle and calculate its distance, and in turn I can check the sign of that distance to determine whether it's an inside point or an outside point, and I'll simultaneously increase the relevant count. I've done that for point 1 of the triangle, I can do it for point 2, and finally point 3. So this will leave me with two arrays. One will be part filled with inside points and one will be part filled with outside points. And notice that these are pointers to points. Now it's time to classify the triangle. If my inside point count is 0, then the entire triangle has to lie on the outside of the plane. So my function is going to return 0. There will be no valid triangles. In the completely opposite sense, if my inside point count is 3, then all of my points lie on the inside of the plane. So I'm just going to set one of my output triangles to be equal to my input triangle, and inform the caller of the function that only one of these triangles is valid. If I have one inside point and two outside points, I'm going to be returning a new, smaller triangle. So I'm going to copy over the input triangle's parameters to the new output triangle, and then construct the two new points. Of course, one of the points is already on the inside, but the two new ones are at the point where the line along the edge of the triangle intersects with the plane we're clipping against. In a similar way, if I've got two inside points and one outside point, I'm forming a quad, so I need to create two new triangles. I copy over their information, and then I set their points accordingly, as we've just seen in the slides, and inform the caller of the function that both triangles are now valid. So how do we know what to clip against? Well, clearly we don't want triangles to get too close to the camera, or indeed go behind it. So I think a plane just in front of the camera, our near plane in the projection matrix, might be a good starting point. So if you remember our projection matrix, we end up creating what is called a frustum, which looks into our world, and we defined a near plane and a far plane and a field of view. So I think taking this plane would be a good starting point, and it's quite easy to calculate the position and normal for that plane. So any triangle that is visible but goes in front of that plane gets chopped up and cleaned up for us, so we have no triangles going in front of this plane. But whilst I'm sketching this out, we can also think about what's happening at the sides of the screen. We could also clip against this plane and this plane, because in principle these two lines represent the horizontal boundaries of the screen, and also the top and bottom, depending on how we're looking at this. However, I'm not going to do that, and that's a deliberate choice. This is actually a very useful way to do things, because you could check whole objects whether they're inside the viewing frustum or not, and from that we can decide, do we carry on drawing them. But I'd like in this video to demonstrate that we can clip in world space and in screen space. So for now, we're just going to focus on world space clipping as the Z approaches the camera. Now, some of you might be thinking, why can't we do the Z clipping once we've projected the triangle? Well, simply, we've lost the Z information at that point. So we have to do depth clipping in world space. But fortunately, because we've transformed by the view matrix, we don't need to work out where the plane is in world space, because we know it's always just in front of the camera. And since we've done the transform with the look at matrix, this is a very easy location to determine. So given the algorithm that we've just seen in the slides, I'm going to create a small array that holds two clipped triangles. And I'm going to clip the recently viewed triangle against a plane. And the plane is going to be defined as being a point that is on the near plane, so this is just in front of the camera along the z-axis, and the normal is indeed straight along the z-axis. And because we're doing this in view space, this is very easy to calculate. And this will populate the two elements of my clipped array accordingly. It could be that both of these contain nothing after the clipping function. But we can't make that assumption, So now I need to choose how to project the two clipped triangles. A small loop will allow me to go through all of the triangles that now exist for the main triangle we were trying to clip. So this could be 0, 1 or 2. But I'm no longer looking at my try_viewed variable. Instead, I want to change this to my clipped array element. Nothing else here needs to change, because we'll take now our clipped triangle that becomes projected, and we'll add it to our vector of triangles to raster. Before we test this, I'm also going to get it to draw the wireframe of the triangles, so we can see what's going on. Let's take a look. So there's our model. I'll just elevate us a little bit. And as I approach the model, well, we're getting some slowdown. It's not quite working. But let's look at it from a different perspective. To start travelling along the x-axis. Try and get the camera right down so we can see what's happening. It seems quite happy with that. We're not getting any problems, but I'm less convinced that it's working. Just to make sure things are happening, I'm going to set the point on our clipping plane to be quite some distance in front of us. And straight away we can see the triangles being clipped. It gives us like a constant black border around the screen. So I'm quite happy that the clipping routine is working. And in fact we can see as we travel along the x-axis here how it's working. Let's just remember to put that back. I think I'd like to temporarily alter our clipping routine so we can see which triangles are being clipped and how they're being clipped. And to do this, I'm just simply going to force the colour of a triangle. So if it gets clipped into a smaller triangle, the triangle is going to become blue. But if we're going to split into a quad, I'm going to set those to green and red. This is just temporary. So I'll move along, move up, and start walking into the scene. So we can see blue triangles, red triangles and green triangles. And this is clearly a quad now, the green and red triangle making up the boundary of the quad, whereas the blue is a single triangle. We're still getting performance stutters as we approach the screen, and that's because we still have very large triangles which aren't clipped against the edges of the screen, so I think it's time to do this. We've just implemented a routine that clipped against a single plane in the z-axis. We can do exactly the same code to clip against the screen edges, but we want to do this when we're rasterizing the triangles. So I'm going to change this routine a little bit. Instead of try projected, I'm going to call this try to raster. And just like we did before, I'm going to create a small array, and I'm going to add now the queue that we talked about in the slides. I'm implementing my queue with a standard list. And just as the pseudocode dictated, I'm going to test for each plane and for each triangle in the queue against the planes. And I'll have a list of new triangles which I replace my queue with. I don't need to sort these triangles or anything, they've not changed relative on Z, and nor have their colours or any other properties about them changed, so I'm just going to draw them straight away. And I can do that now with a little for loop that iterates through the list of new triangles. I'll also include the wireframe drawing code too. So the rastering loop has changed a little bit to include clipping against the screen edges. And the screen edges are quite easy to determine because along the top it's simply 0, 0, 0. That's a guaranteed point along the plane that represents the top of the screen. And we'll have a normal pointing into the screen. On the bottom we know that the position, because we're in screen space now, is screen height. That is a point that exists on the plane. But our normal is -1. It's going from the bottom of the screen to the middle. And likewise we have similar stuff for the X planes along the left and right hand edges of the screen. So let's take a look. And we can see straight away that the clipping is working against the edges of the screen. As we move backwards and forwards, let's move to we're not clipping at all, we can see the whole model, but as we start to move in, the triangles get clipped. And we can see the quad is now formed out of the red and green triangle, and the single triangle on its own is smaller, becomes blue. And we don't notice any kind of slowdown or performance hits because we're now in complete control of our triangles. So if I move up and rotate a little bit, we can start to see that actually behind the scenes there's all sorts of triangle manipulations taking place, just to ensure that we can render smoothly and consistently. Here I've created a fairly low resolution, low polygon count bit of level. I don't know, it's a platform with some walls around the outside. But I thought it nicely demonstrates how we're clipping against the different edges. So I've got my first person camera and we can see how the whole level is distorted according to what's necessary to facilitate the clipping. As I move the camera forward, we can see the triangles distorting in real time. And I think this is really fascinating to think that games are doing this and you just have no idea that it's doing it. Since we've now got the ability to render quite detailed objects accurately and consistently, I thought I'd really try a high polygon model. So I think this model has about 5,000 polygons in it. It's of the same level we've just seen, but just at a much higher level of detail. And the grid on the floor makes it quite possible for us to see the frustum of projection. It's a bit like some sort of grim console disco, isn't it? And finally, after some creative blendering, we can create really large objects. So this is many thousands of polygons spread over a large area. I wouldn't recommend that you construct game levels in this manner, but nonetheless, I think it's quite a pleasing result. I think seeing the clipping is getting a little bit distracting now. So I'm going to disable the debug colouring and not draw the wireframe. I'm also keen to see how well it performs, so I'm going to compile it in release mode. And it seems to be quite happy, on my machine at least, to be running about 430 frames per second. And I think this is very smooth, very nice. I'm quite pleased with how this project has turned out. And so there you have it, a 3D graphics engine running in the command prompt, coded completely from scratch. I know quite a few of you have been asking about texturing, and I don't know yet whether I want to do a part 4 for this series. Simply because the console doesn't have very many colours to choose from, so I'm a bit worried about the spatial resolution and colour resolution not yielding a very interesting result, particularly when you think you've got to merge textures with lighting. However, I will have a bit of an experiment with it. It's certainly possible to do something. What I'm more excited about with this engine is we now have an established platform for thinking about other things in 3 dimensions, so we can perhaps think about 3D physics or collision algorithms. Anyway, the source code is available on GitHub as always. Have a think about joining the Discord server and discussing the engine, or ask me any questions you've got about it. I'm sure there's quite a few. I know that this video has been very quick. It's only because there's a lot of material to cover and I didn't want the video to be too long. If you've enjoyed the video, give me a big thumbs up, have a think about subscribing, and I'll see you next time. Take care.